Hey, what's up guys, it's Jess. Welcome back to my channel. This is not my usual content, but I figured I might as well post a video on it since it is very applicable. I have a Earth and Space Science final this upcoming Wednesday, so I thought why not make a YouTube video going over final exam concepts that we need to know. If you happen to be taking ESS 102 at UW or another university, this video is for you to prepare for the final exam. It's also for me to prepare for the final exam. Basically, I'm going to go over key concepts and questions from all of the lectures and labs and stuff like that, and then go over the final review problems that we were given by the TA. Okay, I might as well just go ahead and get started because I have to study for my math exam after this. The first topic we learned was scientific notation. Scientific notation is pretty simple as long as you keep track of all the rules. As you can see at the top, 4,275,000,000 just becomes 4.275 times 10 to the ninth. You just pretty much move the decimal place. As you can see, you start at 4, move it over a couple times, you'll reach 10 to the ninth. Next, you're going to have something like 0.000374. Same thing. You just move the decimal place over until you reach that first number, except for this time it's going to be negative because the zeros are in front. Next thing you might see is what happens when you're multiplying. So basically what you do is you're going to add the exponents. So 10 to the 3 times 10 to the negative 9 is just 10 to the 3 plus negative 9. So then your final answer is going to be 10 to the negative 6. Next, you're going to have division. So 10 to the 3 divided by 10 to the negative 9, you're just subtracting. So that's going to be 10 to the 3 minus negative 9 equals 10 to the 12. Next, you're going to have exponents that are multiplied together. And in those cases, you will multiply those exponents. So 10 to the third to the power of 2 is going to be 10 to the 3 times 2, which is 10 to the 6th. Let's say you have 5 divided by 10 to the 2. You're going to have 5 times 10 to the negative 2, which is 0.05. Next thing you might get into is adding numbers in scientific notation. So let's say you have 3.0 times 10 to the second plus 2.6 times 10 to the 5. What you're going to do there is try and get a common 10 to the power of whatever. So in this example, I chose 10 to the 5th to be that thing that they share in common. And so what you're going to do is just change whatever number that didn't have 10 to the 5th and make it so that it is multiplied by 10 to the 5th. So 3.0 times 10 squared becomes 0.003 times 10 to the 5th. Those are the same exact number. If you ever get confused on how to convert them, just imagine like what 3 times 10 to the 2 is. That's 300. And then from there, you think, okay, how can I get this to be 10 to the 5th? And then go from there. Now what you're going to do is you're going to add that 0.003 plus that 2.6 that was in front of the 10 to the 5th anyway in the first place. Add those together, and then that number multiplied by 10 to the 5th is going to be your final answer. So in this case, it's going to be 2.603 times 10 to the 5th. The other example is if you are subtracting and you're going to do a very similar process where you're going to try and get that common 10 to the power of whatever. So in this case, let's say you have 1.0 times 10 to the 5th minus 7.0 times 10 to the 2. What you're going to do is change that 7.0 times 10 to the 2 number to have it be multiplied by 10 to the 5th. So that's 0.07 times 10 to the 5th. You subtract the two numbers in front, and that is going to be times 10 to the 5th, and that's going to be your final answer. So you're going to have 1 minus 0.07, which is 0.993 times 10 to the 5th, and that is your final answer. That's pretty much all of the rules you need to follow for scientific notation. So now we're going to get into the specific questions that they have asked throughout the year. One question is, how long does light take to travel from the visible surface of the sun to the earth? You might have to do some conversions on the final exam, so that's what we're going to do first. We're just going to change distance from kilometers into meters, and what you need to know there is just the conversion factor, that 1,000 meters are in 1 kilometer. Solve that, you're going to get 1.5 times 10 to the 11th meters. From there, you need to recognize that you need to use the speed equation, and speed equals distance over time. All you need to do is switch it around a little bit, solving that and using our scientific notation rules from before and converting into minutes as well. You're going to get a final answer of 8.3 minutes. Next question is, how far is Voyager if it takes 20 hours and 30 minutes to receive a signal from it? What you're going to do here is use the speed equation again. So speed equals d over t. Then you're going to get d equals t times speed. Plug in your speed as 3 times 10 to the 8th meters per second. Plug in your time that you solved for. Get a final answer for distance, and then convert it to AU. Next topic is going to be about the solar system and the universe. The first subtopic we're going to get into is general scale. So the first question, how big is the universe? The universe is infinite. How big is the observable universe, however? That is 93 billion light years. And remember, light years is a measure of distance, not time. Next, how big is the Earth? You can just say its radius is 3,958.8 miles, roughly. And how big is the sun? If you're looking at it in terms of radius, that's going to be 432,690 miles, roughly. The next question is, how do stars and solar systems form? And stars form by gravitational collapse of hydrogen-rich gas clouds. So when density becomes high enough, nuclear fusion starts, and that's when they start to emit their own light. Solar systems form when a dense cloud of interstellar gas and dust collapses to form an accretion disk. Next question, what type of stars are out there? So if you're looking at it from decreasing temperature, you're going to have O, B, A, F, G, K, and M. But you're also going to have categories like main sequence stars, giant stars, white dwarfs, and supergiant stars. Next question, what types of planets are there? There's going to be things like rocky metal planets, and there's going to be gas and ice giants. Next question, what is differentiation and when does it happen? Differentiation is the compositional evolution of a planet driven by gravity, and it needs to be big enough to have enough gravity. Heavier elements migrate toward the surface, and this happens at the protoplanet stage when gravity is enough. What is the internal structure of planets? So this is where a diagram is really helpful. As you can see here, there's a crust, there's a mantle, there's the liquid iron outer core, there's a solid inner core. So another thing you have to look into is the density and the ingredients that the planet formed with. Rocky planets generally have a metal core, a rocky mantle, and surface. Gas and ice giants usually have a metal or rocky core, but they have gas, fluid, ice envelopes. The next topic is light, and so that gets into the question of what is light. So first thing you're going to do is look at its properties, and that's going to be energy, power, intensity, wavelength, frequency, and speed. So light has both wave and particle properties. The wave, you can say diffraction, particle, you can say photoelectric effect. And light also travels as an electromagnetic wave. The next question is, what is a photon? And a photon is the smallest bundle of electromagnetic energy. A photon's energy is proportional to its frequency, but it's inversely proportional to wavelength. And the equation you would use here is E subscript P equals HF, which equals HC over wavelength. Next question, what are the aspects of wave? Wavelength is the distance between two consecutive peaks. Peak amplitude is the height of the wave, and that's related to intensity. Speed is the distance of movement per unit time. Frequency is the number of peaks that pass a location in a given time. So when you're looking at a shorter wavelength has the same speed, but it's going to have a higher frequency and a higher energy. For most wavelength questions, you're probably going to be using the frequency equals C over wavelength equation. Next question, what is an absorption spectrum? And they're definitely going to ask this on the exam, so just make sure you know it. This requires a cool object in front of a hot background. Imagine a rainbow, and then you're going to see black lines in certain spots. Next question, how do we use spectra to learn about objects? What it does is it tells us the temperature and composition of certain objects. Next, we're going to be describing the electromagnetic spectrum, and going from long wavelength to short wavelength, you're going to have radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. What the EM spectrum is a distribution of intensity as a function of wavelength or frequency or energy. Next question, black body spectrum is continuous. What does it depend on? The answer is temperature. Next question, what is an emission spectrum? Emission spectrums require a hot object with a cool background. It's also discrete as well. What you're going to see is a black background with a few colorful lines spread out. Next, we're going to get into the topic of matter. First question, what is the structure of the atom? What is the history and current ideas? So one of the models is the plum pudding model. This is where an atom has smaller components. There's negatively charged corpuscles, plums, positive soup to balanced charge, which is the pudding. So an atom is a large neutral entity with positive and negative charges mixed together. Atoms are mostly empty space, and positive charges are very localized. Next is Rutherford's atom, and this is where mass is highly concentrated in the positively charged nucleus at the center of the atom. Electrons orbit the nucleus, lots of empty space in between, and it's similar to the modern model in that the number of protons determines the element's identity and the number of electrons determines its chemical properties. Next is the Bohr atomic model, and that is a quantized structure of electron orbits in an atom, and they also show spacing between energy levels is not even. Next question, what makes elements, isotopes, and ions different? Atoms with the same number of protons are atoms of the same element. Atoms of the same element with different numbers of neutrons are different isotopes of that element. Isotopes of an element have the same chemical properties but different masses, different emission spectra, and different behavior during nuclear reactions. When an atom absorbs light or thermal energy greater than the binding energy, the electron escapes, and the atom is left with a positive charge, and that's called an ion. And an element is a substance that can't be broken down by chemical means. Next question, I'm feeling a little parched. I need to drink some water. Alrighty, next question, what are subatomic particles? This includes protons, neutrons, electrons, positrons, neutrinos, and photons. Next question, what are the different types of radiation and how does each type affect or penetrate matter? Alpha is kind of like the weak sauce of the group. Next one is beta, might see them at the gym once or twice a week, max. Gamma is a type of radiation you see at the gym 7 days a week, no rest days, therefore at least 2 hours minimum. Next, we're going to get into the sun, and the first subtopic is solar interior. The first question is, how does temperature, density, and pressure vary with depth? Basically, it increases with increasing depth. Next question, describe the core, radiative zone, and convective zone. The core is 20 to 25% of the radius, and it extends out to 0.2 radius of the sun. This is where the proton-proton reaction happens, where the fusion happens, and it contains 50% of the sun's mass and 2% of its volume. Also bounded by the point where temperature and density are too low to support the proton-proton fusion. Next, we get into the radiative zone, and this is up to 70% our sun. So it extends from 0.2 to 0.7 our sun. This contains 48% of the sun's mass and 32% of its volume. It also contains free electrons and atomic nuclei, so plasma. The radiative zone is bounded by the point where temperature and density are low enough to permit atoms to hold their electrons, and this is where convection starts. Then you get into the convective zone. This goes up to the surface, so it extends from 0.7 to 1 radius of the sun. The transition from radiation to convection happens in the tachycline, where the sun's magnetic field is supposed to originate. Next question. What powers the sun? What is fission? What is fusion? And what is a chain reaction? Fusion is what powers the sun. Both fission and fusion are nuclear reactions that produce energy. Fission is the splitting of a heavy, unstable nucleus into two lighter nuclei. Fusion is where two light nuclei combine together, which releases vast amounts of energy. The proton-proton chain reaction is a sequence of nuclear fusion reactions where hydrogen is burned to convert to helium. Next subtopic is solar activity. The first question is, what are sunspots? Sunspots are transient features in the solar atmosphere, and it's paired on the surface of the sun. They're connected to filaments on the surface, and they're clustered near middle regions of the sun and rotate with it. They're also cooler than surrounding areas. Next question, what are solar flares? They occur in regions of rapid magnetic field realignment, X-ray and UV bursts of radiation associated with strong changes in the magnetic field of the sun. They're often associated with coronal mass ejections, and they can last up to an hour. They also release massive amounts of energy. Next question, what does convection look like? Miso soup is the answer. Why does it happen? It's when you heat from the bottom and then cool from the top. Higher density will make convection more effective than radiation because plasma is not dense enough to transport heat via radiation. Next question, what effect does solar wind have on the solar system, planets, and spacecrafts? Solar system affects planets' magnetospheres and their atmospheres. Atmospheric escape is driven by solar wind. Solar wind can dramatically change a planet's surface. It can also increase drag on low Earth orbit spacecraft. Next question. Oh, hopefully we're making it to the end. How does the sun's heat and intensity decrease with distance? This is an equation. It's intensity of a planet equals L sun over 4 pi distance squared. Distance increases as intensity decreases. Next topic is orbital mechanics. The first question is, what are Kepler's laws? The first of Kepler's laws is planets move in elliptical orbits with the sun at one focus of the ellipse. The second law is the orbital speed of a planet varies such that a line joining the sun and the planet will sweep equal areas in equal time intervals. Orbital speed is faster when it's closer to the orbital body. Kepler's third law is an equation, and that is p squared equals ka cubed. The k is sometimes omitted. P is in units of years, and A is in units of AU. Next question, what are the pieces of an ellipse? Periapsis is the closest approach, and apoapsis is the highest altitude. If you're drawing an ellipse, you'll see that the apoapsis is at one end of the major axis, and the periapsis is at the other end of the major axis. The minor axis is just, the smaller axis. The distance between the center of the ellipse and that focal point is C. That's the C you use in eccentricity. And A is the semi-major axis. Next subtopic is gravity. What is Newton's law? That's just F equals G, M1, M2 over R squared. Next question, what is escape velocity and what happens when an object achieves it? It's the speed necessary at a given altitude to escape the gravitational influence of an object. So kinetic energy needs to be higher than potential energy to escape a planet's gravity. The escape velocity equation equals the square root of 2gm over r plus h. Okay, number 4, what is gravitational assist? This is used to increase or decrease velocity and change direction. It also relies on relative motion of a planet in spacecraft. It saves a lot on fuel. It allows more mass to be sent for a longer travel time. What are the types of orbits? Low Earth orbit is 1, LEO. This is under 2,000 kilometers for altitude. Next is the medium Earth orbit, MEO. This is 2,000 to 42,000 kilometers. Next is the geosynchronous orbit, the GSO. This is 35,786 kilometers. Next is the high Earth orbit, which is HEO, which is higher than the GSO, and then you're going to have high inclination orbits. How do you change inclination and why? You change inclination when you want to change the plane of an orbit. So it's necessary if you don't launch from the equator and you want an equatorial orbit like a GSO, or you want to look at polar regions. Next question, what are Lagrange points? This says that a small body under the influence of gravity will remain stable. L1, L2, and L3 are unstable equilibrium, whereas L4 and L5 are the stable equilibrium. Next, we are getting into rockets, which I flipping hope is one of our last topics. First question is, what is the conservation of momentum? This is where initial momentum equals final momentum, and the equation for that is velocity of the craft equals mass of fuel times velocity fuel over mass of craft. What are the rocket equations? It's going to be m fuel over m final equals e to the power of change in velocity over ce minus 1. The next equation is change in velocity equals ce times natural log of initial mass divided by final mass. Next question is, why would you use stages? And you use stages because that's the only time you're going to achieve escape velocity. The engine can be adapted to the environment that they are used in. Engine designed for sea level will be less efficient in space, and the engine designed for space will be less efficient at sea level. Another great thing about staging is that you can use fuel with lower thrusts but better efficiency. Next topic is electric and magnetic fields. First question, how do charged particles behave? Charged particles interact via electric fields. Like charges repel, opposite charges attract. Second question, how does a magnetic field cause current and what can generate a field? Moving charged particles, so time variation, are electric currents, and currents generate magnetic fields at 90-degree angles. What planets have magnetic fields? Mars and Venus have very small magnetic fields, and they don't protect the atmosphere from solar wind. Earth, Jupiter, and Saturn have strong, centered, dipolar magnetic fields. Mercury has a small magnetic field, And then Uranus and Neptune have strong magnetic fields, but odd characteristics. So there's high inclination to the rotation axis. There's also offset of the dipolar dynamo. Next question, how do magnetic fields interact with solar wind? Solar wind slows down and changes direction when it interacts with Earth's geomagnetic field on the side away from the sun. And then this field stretches out to become the magnetotail. Next question, what are the Van Allen radiation belts? So this is charged particles trapped by Earth's magnetic field. The outer belt is ions and electrons. The inner belt, high energy protons produced by cosmic rays. Next, we're getting into orbital mechanics. First subtopic, orbital maneuvers. First question, how do orbital maneuvers work and why, when and why would you use them? Change in orbit is going to equal your change in velocity, and this is independent of mass. Orbital maneuvers are useful to change altitude, useful to meet with another spacecraft. You can change eccentricity, you can avoid hazards, and you can pass closer with an interesting object. Next, we're going to look at some options for transfers. The first one is going to be the Hohmann transfer. This is a transfer between two coplanar circular orbits. It requires 2 engine burns, and the lowest energy transfer is if R prime divided by R is less than 12. Next is the bi-elliptic transfer. This is a transfer between 2 coplanar circular orbits, but it requires 3 engine burns, whereas the Hohmann transfer only required 2. This is lower energy than the Hohmann transfer if R prime divided by R is greater than 12. And this you would also assume impulse thrust, and it's a much longer time than the Hohmann transfer. Next, we are getting into rockets. First question, did I skip something? Back to rockets. That was all out of order. Don't know why. Next question. What is thrust? This is force in newtons provided by an engine. And for launch, you're going to need a thrust to weight ratio greater than 1. Next question. What are the types of engines? There's chemical reactions, which is a chemical engine. There are plasma reactions, which is an ion thruster. And then there's nuclear reactions, which is nuclear fusion engines. What is chemical propulsion? Short burn, high thrust. Works by heating a gas through a chemical reaction. There are 3 types of chemical rockets. There's a solid propellant, liquid propellant, and hybrid rockets. The pros of solid propellant is that it's a high thrust at a low cost. The cons are that it's impossible to turn off, and it's also a low exhaust speed compared to the liquid fuel. For liquid propellant, the pros are that it can be turned off, but the cons are that there's low thrust and there's low exhaust speeds, and it's also super toxic. So just think of that really horrible, toxic person from your past and just associate them with liquid propellant. Next question, the 3 types of propellants. 3 types of propellant. There's cryogenic, there's semi-cryogenic, and there's hypergolic. Cryogenic is the best in efficiency, but you need to do short missions because it's not super energetic. Semi-cryogenic is a good efficiency, and it's most energetic, but you also only have to use it for short missions. The hypergolic can be stored for years, and it has an okay efficiency, and it's pretty energetic, but it's also super toxic. So again, next question, what is electric propulsion? Fuel is heated by electricity until ionization. Plasma is accelerated using electricity. It's fired for a long time and it has a low thrust. Next question, what are the types of thrusters and when would you use each engine and thruster? What are the main components of each type of engine design? So an electromagnetic hall thruster can be used for station keeping, orbital transfer, and primary propulsion. The advantages are that there's a high exhaust velocity, there's a simple power supply, and there's a high efficiency. But the cons is that there's a wide beam divergence and there's going to be lifetime issues with erosion. How they work is that there's a current that interacts with radial magnetic field to accelerate ions. Next is the pulsed plasma thruster, and this is the electromagnetic category. It's used for station keeping and small nanosat. The pros are that there's a simple design, it's a low power, and it's a solid fuel. But the cons is that there's low thrust, low efficiency, and it's toxic. How it works is it just accelerates plasma. Next is the iron thrusters in the category of electrostatic. It's used for station keeping, orbital transfer, and main propulsion for deep space probes. Its pros is that there's a high exhaust velocity and a high efficiency, but the cons is that there's low thrust, it's a complex build and power processing, grid and cathode are eroded over use, and there's also high voltage. Next is electrothermal, and it's used for station keeping and orbit insertion. The advantages are that it's scalable to high power levels, it's a simple design, low voltage, and can use hydrazine. But the disadvantages are that it relies complex power processing, electrode erosion, there's high current, which produces waste heat, and it requires durable wiring. Oh my gosh, we're almost done. Next topic is robotic versus human exploration. What are the effects of extraplanetary conditions on humans? There is a lot. The main ones are radiation, the space environment, which is pressure and temperature. Like, you really have to worry about pressure and temperature. High accelerations and weightlessness, and psychological hazards. The psychological hazards includes poor sleep. There's stress, which can result in mental health problems, and there's also isolation and confinement. Among these, there is also disruption of sense and habits. There's also puffy face syndrome, which has to deal with blood circulation. You also have to deal with fluid redistribution. You have to deal with bone and muscle structure, and also motion sickness. A lot of these reasons are why I will never ever become an astronaut unless the world depends on me. Next, what types of missions are best suited for different objectives? A flyby is where you pass in close proximity of an object. You can explore several bodies in a single mission, and it's easy to design and operate trajectory, so this is usually used as a first mission. An orbiter is used for long-term access to an object, and you can also observe temporal evolution. This is usually done after a flyby mission to provide a more comprehensive coverage of the body. An atmospheric probe is direct tasting of the atmosphere, and this is generally brought by an orbiter or a flyby mission. Next is the lander, and this is direct tasting of the surface composition and its features. You can also observe temporal evolution. Many are used to prepare for human landing, and it can be brought by an orbiter or flyby mission. Next question is, what are some of the historical missions talked about in class? One of them is Mariner 2, which is the first planetary flyby. Next is the USSR's Luna 3, and this is the first moon flyby in 1959. It's also the first gravitational assist, and it was also the first far side picture. Mariner 9 is the first planetary orbiter. Venera 7 is the first planetary landing. Mars 3 is the first planetary rover. Next question is, what are power systems? So you're going to have solar, RTG, and nuclear. Solar is good when possible because it's currently the best efficiency at 32% of incoming power. RTG is electricity by the thermoelectric effect, and you use a radioactive source. You also need a cold source. It's very sturdy, it's smaller and lighter than solar, and it also provides constant power as well. Next question is, what do craters tell us about a surface? So moon mares are younger than the mountainous areas, so the places that are younger have less craters, and the places that are older have lots of craters. So that was it for the complete study guide, and now we are going into the review problems. The first question is, what is the amount of solar intensity received at this location in watts per meter squared? And again, you're given like certain values. When you get a problem like this, you should recognize that you're going to use the intensity equals power over S equation. Solve for S by knowing it's 4 pi r squared, and then just make sure you keep track of your units and you're good to go. Next, what is the frequency in terahertz of an electromagnetic radiation with a 454 nanometer wavelength? When you see frequency and wavelength, you just know to use the frequency equation, which is F equals C over wavelength. Again, keep track of your units and you should be good to go there. Hofer lines, black bars in the sun EM spectra are created by. They're created by photon absorption, and this is by electron excitation, which is not ionization. A discrete emission line of a hot gas is due to what? The answer is electrons falling back on a lower energy level by emitting a single energy photon. Next question. What type of detector should you put on a satellite to survey the sun's solar flares? You're going to be using an X-ray detector. When the high velocity plasma from a coronal mass ejection reaches Earth, this can create a geomagnetic storm. What is the orbital period of a trans-Neptunian object located at 161 AU from the sun in years? This is where you use Kepler's third law of p squared equals a cubed. Plug it in, you're good to go. Next question. For a spacecraft high above Earth atmosphere, if no modification is applied, what will happen? The spacecraft is just going to stay in orbit indefinitely. There's going to be no change in speed either. Next question. What is the most fuel-efficient way to do the interplanetary travel? And what is the most used trajectory strategy to maximize efficiency? That's gravitational assist. Nuclear thermal propulsion has larger exhaust speed, but lower thrust than chemical engines. Next question. If I want to study the evolution of the global Mars atmosphere over several years, which type of mission should I choose? You should choose an orbiter. Next question. Would you use chemical or electric propulsion to travel to another star? You would use electric propulsion. Chemical is good for launches because it has a higher thrust. Why is it difficult to do a Hohmann transfer with electric propulsion? Hohmann transfers require discrete burns and pushes at the right times, and it also takes a super long time to build up speed. Next question. A mission to Titan plans to use a rotocraft. Why would this be a bad idea for studying Europa, which is another icy moon? The answer is that a rotocraft flies around and it requires air for it to work, and you need an atmosphere. You're not going to get that with Europa. Next question, is the ISS going faster, slower, or equal to Earth's escape velocity? The ISS is going slower than the escape velocity. Earth's orbital period is 1 year and its orbital radius is 1 AU. If it had half this orbital radius, how much faster would it be moving? Okay, here you would use Kepler's third law, p squared equals a cubed. Other important things to note with the answer to this question is that planets farther out are moving faster even though they take longer to do a full orbit. Next question, what type of spectrum can a rover like Perseverance use to determine the composition of Mars' atmosphere? You're going to use absorption because Mars' atmosphere is super cold and the sun provides a hot background. So you wouldn't use an emission spectrum or a black body spectrum. Next question, a small asteroid is primarily made of iron. What can we infer about its history? Solar nebula collapses into star/protoplanetary disks, and this has rocky bits, ice bits, and gases. The rocky body has two components, which is iron and silicates, and the large bodies differentiate. An asteroid must also be a broken piece of another body's core. If you launched a spacecraft from Earth, how fast would it need to be going to escape the solar system with no further propulsion? When you see escape in the question, always think to use the escape velocity equation, which again is equal to square root of 2 gm over r. A rocket using LOX and liquid H2 is cryogenic, but if it uses LOX and kerosene, it is semi-cryogenic. What's the difference? So this refers to the storage temperature of the fuel. These are liquid fuels. Both need to be kept cold for cryogenic, but only one of them needs to be kept cold for semi-cryogenic. It's also easier to store warmer fuel, and semi is easier than cryogenic, but hypergolic is even easier than both of those. Cryogenic is the most efficient, but it's the least energetic. That was the end of my review for ESS 102. Again, if you're taking this course, hopefully that helped you prepare for the final. If you're not taking this course, hopefully you learned something about space. Do you want to say hi, Bailey? To my 200-something subscribers? No. Okay. I hope you guys enjoyed, and I will see you guys in my next video. Bye!